Okay, good evening everybody and welcome to my inaugural lecture. I'd like to start by thanking the members of the VCPB for inviting me to undertake this lecture. I'd also like to thank members of the School of Sport for attending and people that have travelled from around the country and from across Europe to come and attend the lecture today. We do actually have colleagues in the Czech Republic who are Skyping in and watching the lecture as well. So thank you very much for attending. My talk is going to look at and outline the main themes, topics and focuses of my research over the last 15 years. I'm going to touch on some specific examples, particularly within technique selection and artistic gymnastics. I'm going to look at how the physical environment and changing the physical environment can influence sports performance and alter the risk of injury with the introduction of 3G turf. And then finally, I'm going to look at some take-home messages and some summaries of my research. Throughout the lecture, which should last about 40 to 45 minutes, hopefully, I'm going to try and focus on the question, can we impact on performance? From the beginning, really, my interest in sport and sports science has come from trying to understand and explain sporting performance, using grounded scientific methods to address meaningful questions that inform coaches, scientists, and clinicians. And there are two main approaches that I've taken. Firstly, the coaching biomechanics interface, and secondly, sports medicine and injury. On the left-hand side, I've examined questions associated with identifying the conditions that create successful technique. Also looked at how we can identify what the most effective and efficient techniques are in terms of skills that are performed with a variety of techniques, and trying to remove the trial and error in terms of skill development and the coaching process. On the right-hand side, in terms of sports medicine and injury, I've tried to identify, firstly, driven by the injuries that occur, often from epidemiological perspectives, to try and understand the mechanisms of injury and identify the risk factors that may predispose athletes to the occurrence of injuries. In addition to that, I've looked at the biological failure due to abnormal segmental orientations and loads during sporting performance. But I can confidently say most of my research has been focused on this, the coaching biomechanics interface. And it's kind of built, as Sheldon said, from my interest and my experiences as a coach and as a performer in the sport of gymnastics. And two of the first papers I produced were based on, strangely enough, qualitative type data. And first of all, I identified that coaches, in terms of understanding technique and understanding performance, develop a conceptual understanding, a mindset of how a skill works. And this is based on knowledge, experience, and technical awareness. Technique awareness is really when a coach talks about movement patterns, body positions, and the decisions that they make that inform their decisions in terms of training come from this mindset. So this mindset allows them to understand the technical aspects of skill, particularly in terms of how the skill is broken down and what the key and the functional phases of skills are. From this, they aim to develop skill by replicating the spatial and temporal characteristics of the skill they're trying to learn in the drills that they're producing. So the spatial and temporal characteristics being the movement patterns and the timings of those skills. And from this, drills can be optimized and individualized, and the development of skill, particularly within sport gymnastics, occurs. This then feeds back to increasing experiences, knowledge, and technical awareness. And this is really how biomechanics fits into the coaching process in terms of us understanding and explaining how performance is achieved. From this technical understanding, adding to that the correlates of the biomechanical determinants of performance provides us with the opportunity to develop training drills, skill development, and strength and conditioning regimes that are effective, efficient, and safe. And that's really a large portion of the research that I've done has been focused on achieving that. There have been four main topics of my research: technique selection, skill development, motor control, and physical environment. In terms of technique selection, this has really addressed questions such as, what are the best techniques? And can we identify the best techniques to perform certain skills that may improve performance and reduce injury? Examples include research that we've undertaken with the Czech Olympic team at the University of Ostrava, examining different hand positions in fundamental skills such as the round-off. And we've identified that certain hand positions predispose performers to lesions at the wrists and elbows and shoulders. Other research in this area has included identifying which of the different techniques that are used to perform this skill, the long swing on uneven bars in female gymnastics, where we have a female performing 3 different styles of this skill. In this one, the gymnast performs an arch position followed by a pike position followed by a straddle position. And coaches are really set with the challenge of identifying which of these is the best one to use and what the influences of those are. This research is the focus of Michelle Manning's PhD, who submitted a PhD today. She's somewhere in the room, so congratulations to her. In terms of skill development, this really is linked to technique selection. And I tries to identify how we develop skills and how we learn in terms of progressing skills and linking biomechanics and the training theory together, with the aim of making training more effective and efficient. With colleagues at the University of Sao Paulo, we've focused research on developing strength and conditioning exercises for men's gymnastics, and also work with the Sports Council for Wales now, looking at trying to identify the most effective and efficient strength and conditioning exercises for the development of skills like sprinting and sprint starting. Motor control has really taken this to another level now, trying to understand how humans interact with their environment, trying to understand how the environment, the task or the skill that they're undertaking, and the organism themselves, the actual athletes, control their performance. It expands the theoretical links to the dynamical systems and the self-organization theory, and allows us to take this holistic perspective of performance. The graph at the bottom that's rotating is a visual representation of the coordination of somebody performing a skill. And we can use this as a diagnostic tool for the occurrence of injury and as a diagnostic tool. And finally, the physical environment. We've examined the influence of the introduction of 3G turf into sports such as football and rugby. And we've identified and tried to help manufacturers in terms of this introduction in global sporting policy. At the bottom, I've put a list of the collaborators that have made all of this research possible. None of this research is just done by myself, and they include a number of universities, international governing bodies, and national governing bodies. So I'm going to give 2 examples, one from technique selection and one from the physical environment. In terms of technique selection, what we know is that a principal desire of coaches, scientists, and clinicians is to prepare, nurture, and develop our athletes in order to make them robust, adaptive, primed, and self-aware. Hopefully, this will then lead to programs that are individualized, optimal, safe, and effective. Gymnastic coaches are set with a challenge in terms of which techniques to select in order to optimize performance. So the questions that emerge are, what are the most effective techniques? Does the choice of technique influence future skill development? And also, do certain techniques increase the risk of injury? And I'm going to touch on the first 2 in this talk. The skill that I'm going to use to explain this or illustrate this example is this one. It's called a Ketchup. It's an interesting skill for 2 reasons. Firstly, because during the skill itself, the gymnast reverses their direction of rotation, their angular momentum, in order to travel safely backwards over the bar to catch the bar. Males perform this skill and female gymnasts perform this skill, although in female gymnastics, the challenge of performing this skill in a straight body position, the more complex version, is still rather elusive. The second reason it's an interesting skill is that it emerged out of the former Soviet Union. In the 1960s, when the Soviet Union decided to use gymnastics as a shopping window for their social and cultural ideals, they brought all of their sports scientists together to come up with theoretically skills that could potentially be produced. So based on the underlying laws of human movement, a Russian methodologist and biomechanist called Smilevsky invented this skill. It was later performed by a Russian gymnast called Alexander Ketchup in 1977, and then later in the 1980s was performed by female gymnasts. It's a skill that's commonplace now in gymnastics, and it's become more common over the last decade for two main reasons. Firstly, the marking criteria. The international governing body has changed the marking criteria to reward gymnasts for performing this skill. And also the apparatus. After the 1996 Olympic Games, the apparatus went from 1.6 meters distance apart to 1.8 meters distance apart. This allowed principally the female gymnasts to swing more freely like their male counterparts and potentially produce the release conditions to allow them to do more complex versions of this skill. Soon after this separation increase, a new technique emerged. So here we have a video, and on the left-hand side, we have the old version, the outward version of the Ketchup, where the female gymnast has to negotiate the low bar on the descending phase. And on the right-hand side, we have the newer version, the inward Ketchup, where the gymnast has to negotiate the bar on the upward phase. And a principal question that coaches wanted to know was which one of these two techniques is more effective and which one can potentially allow us to perform more complex skills. So we undertook a study to quantify the biomechanical differences between these two techniques and try and identify whether they were equally demanding and whether one was potentially more able to produce more complex skills in the future. The relevance of this came from three areas. Firstly, from coaching, understanding the key aspects of the skill and feeding back into the coaching biomechanics interface. In terms of physical preparation and identifying the specific requirements of physical preparation. And finally, in terms of the FIG and their desire to try and quantify skills of a similar name in order to make the marking criteria more objective and more clear. So we collected data at the 2000 Olympic Games and the 2007 World Championships. The data was collected with video cameras of high quality at a frequency of 50 hertz. We then reconstructed the performer using a method known as direct linear transformation to allow us to measure the joint angles and joint and body positions as accurately as possible. The body was modeled as a series of linked segments, and our initial studies looked at identifying how the hips, shoulders, and knees changed during these performances. We know from previous research, though, that the key joints in this skill are the hips and the shoulders. Because we know when a gymnast is hanging on the bar, the forces at their toes are zero because they're not in contact with anything, we were able to apply Newton's second law of linear and angular motion to produce a process known as inverse dynamics to calculate the net joint torques or the net joint moments around the knees, hips, and shoulders. This allowed us then to work out the joint powers and the joint works. And the joint works really can be just considered as the physical demand placed on the performer, how much mechanical work the gymnast had to do. The skill of the Ketchup is based on the fact of the gymnast doing this swing beforehand, though. This is known as the long swing. And the gymnast starts in the left-hand side and rotates back round to the bottom right. And during this phase, there's a position where the gymnast moves from this arch to disc shape, from a position of shoulder hyperflexion to extension and hip hyperextension to flexion. From previous research that we've undertaken, this functional phase is the phase where 70% of the mechanical work is performed to produce the angular momentum requirements of successful performance. The key variables that we were interested in included the velocity or the speed at which the gymnast was leaving the bar, the angle that the gymnast was leaving the bar, and also the amount of rotation that the gymnast had when they left the bar, known as angular momentum. Angular momentum is particularly important, and this is the equation to calculate it. And because you can see in the equation there's this I and there's this M, that determines the mass of the gymnast and the distribution of that mass. So basically the shape and size of the performer. And because we wanted to compare between different athletes of different sizes, we needed to remove this or normalize this from our data. So we used a different equation to calculate angular momentum and normalize angular momentum. And we came up with these units of straight somersaults per second, which allowed coaches to use, which has been used a lot in the biomechanics literature. We were also interested in the movement patterns at the shoulders and the hips and also the amount of work that the gymnast was performing. Okay, so in terms of what we actually found out, in all the tables I'm about to present, they're in exactly the same order. On the left-hand side, we have the old outward version, and on the right-hand side, we have the inward version. And we compared the key characteristics at release, so these are the values of the variables at release. And the key ones really are how much time the gymnast had in the air. So in the old version, the outward Ketchup, the gymnast actually had more time in the air. They released at an earlier angle as well. But more importantly is this bottom value. And basically, you want this value to be higher. So in this skill, the inward version, the gymnast had a greater capacity to rotate. The amount of rotational capacity that they had during the flighted phase was higher. So in terms of changing your body shape, in terms of producing more complex skills, the inward version would be the one to choose. This is a basic illustration of it. I know it's only one gymnast compared to another gymnast, but you can see that during this skill, where we play them both together, if I stop it at the right point, you can actually see the differences in, firstly, the height of the gymnast in this case, but also the rotation of the gymnast. They're in a much better position in order to regrasp the bar and then potentially do other skills after. One of the other things we were interested in was the amount of work the gymnast was doing. And this is one of the more interesting findings. When we compared the amount of work that was done at the hips and the shoulders between these two different skills, the inward and the outward Ketchup, we noticed that at the hips they were very similar. 90% of the work was positive, 10% was negative. In the inward and outward version at the shoulders, though, this was reversed. So principally, as the gymnast was releasing the bar, in the old outward Ketchup, the gymnast was actually closing their shoulder angle and pulling on the bar. And in the inward Ketchup, the newer version, they were actually extending their shoulders, opening their shoulder angle, and leaving the bar in a different position. So from a physical preparation perspective, this was quite important for a skill that kinematically, movement pattern-wise, looks the same. In 2004, a new Ketchup emerged. And this Ketchup was known as the toe-on Ketchup. And basically, we had a very similar question. Does this variant allow the gymnast to perform more complex skills? If we look at it, the gymnast, in this case, as they swing around the bar, they place their feet or their toes on the bar and then open their hips quickly with a large amount of power to create the angular momentum to perform this skill. So we did exactly the same again. Now we have outward, inward, and the toe-on Ketchup. And what we found was that in terms of the time the gymnast has in the air to perform either more rotation or different shape, there was more time in the toe-on Ketchup. In terms of the amount of rotation that they had, we were starting to see more angular momentum, more rotational capacity in this newer version of the skill. So potentially, we could suggest that you don't really need to learn the outward version. The inward version and the toe-on are fairly similar, and maybe this is a precursor to learning this skill. Particularly when you start looking at the joint work, we have a very similar pattern in what's happening at the shoulders compared to the inward Ketchup. So these two skills seem particularly linked in terms of the shoulders being eccentrically contracted during release. But one of the things that female gymnasts or the female gymnastic community are trying to do at the moment is to try and get to the point where they can produce this skill, the straight Ketchup, where the gymnast keeps their body and shoulders and hips open during the flighted phase. So we collected some data from the same competition, the Olympic Games in 2000 and the World Championships in 2007, and normalized our data, so it allowed us to compare males and females, and look to see whether there were differences between now males and females in terms of these skills. And what we found was, certainly for the flight time, males were able to spend much more time or had much more time in the air. But if we go down to the key variable, angular momentum, we can see that for the straight Ketchup, males are producing much more angular momentum. They have much more capacity to rotate. And although in terms of the toe-on and the straddle Ketchup, the values aren't that different. In 2011, we were involved in a project that looked at female gymnast at the Berlin European Championships, and we saw this skill. And if you look closely enough, she was one of the first gymnasts ever to perform this skill. She actually clips her feet on the bar as she passes over the bar. But it does demonstrate that the potential to perform this skill is there in female gymnastics. So we really try to address why this might be the case. Why are males and females different in terms of performing this skill? And probably the reason is the bar construction. When males swing around the bar, they swing around this big tensile steel stiff apparatus. The energy they put into it, they get back out of it. Females swing around this much less stiff, much more plastic-type apparatus that is a composite wood material that the gymnast has to work much harder in order to generate the same amount of rotation and the same amount of time in the air. So you could suggest that if we wanted to see females produce the skills that the males are producing, it would be the apparatus that would have to change. So in summary of this section, technique selection can influence performance outcome. It also, technique selection of the same skill can identify the specific physical preparations that are required to develop that skill in terms of the musculoskeletal demand and in terms of the kinematics. And it's also interesting that the movement patterns that we see similarities in aren't always replicated in terms of the joint kinetics. And ultimately, what this approach can do is show that how we can evolve skill and make training more effective, efficient, and safe. Okay, so the next story that I have is one of physical environment. I wasn't going to put that slide up, but it took me about an hour to get that little thing to happen, so I thought I was going to use it. It's true. And this one is looking at the physical environment, and it's been some research that we've been doing at UX since around about 2010. Professor Len Noakes, DSc from Cardiff University, David Irwin, and Mike Hughes were the first group that looked at this in terms of the physiological characteristics of turf and the introduction of 3G turf. And then, since then, we've taken more of a biomechanical and psychological approach. Just to point out that this is actually John Rawlins, and this is actually Ian Mitchell, the thinner version. And as we know, the 3G turf has been in the press lately. The FA have given a positive announcement that they're going to allow 3G pitches in every round of the FA Cup during the 2014-2015 seasons. Clubs, the General Secretary Alex Holmes said clubs have become increasingly positive towards the use of 3G turf, particularly in terms of the sustainable running costs and also being able to now retain home advantage in competition. Another positive aspect is that the Women's World Cup is now being played on 3G turf in Canada in 2015. And Greg Dyke, the chairman of the FA, has publicly announced the benefits of this from a grassroots level, which I'll just play for you now. The other part.
So how bad is the problem? 25% of amateur matches in England were cancelled last year due to poor pitches and bad weather. No surprise perhaps when there's just 639 3G pitches compared to the 5,000 World Cup winners Germany boast. The FA also wants to tackle coaching. Only 11,000 here hold qualifications. In Italy, 4 times as many do.
So clearly the benefits from a grassroots level of beginning to emerge from the sport of football. And particularly in rugby now, we have the highest levels of the game being played on 3G turf at English clubs like the Saracens, Newcastle, and in Wales, Cardiff Blues. The flip side to that, though, is that after a Wales match in Andorra, Gareth Bale, the Welsh star, was quoted as saying it was the worst pitch. It was a 3G pitch they played on. It was the worst pitch they've ever played on by far. He can't describe how bad, bobbly and hard the pitch was to deal with. Coleman then was cited as saying it was the primary reason for the side's below par performance, and his heart sank when he arrived at the pitch and saw the quality of it. The flip side of that is that it was a particularly bad 3G pitch rather than just a normal 3G pitch. The England captain, though, in response to FIFA announcing that the World Cup in 2015 was going to be hosted on 3G turf, FIFA would never dream of hosting a men's World Cup on artificial pitches, so why the women's? Are they just being used as guinea pigs? And 40 of the top players have threatened legal action if matches are going to be played on this turf. From the sport of rugby, recently, the Exeter Chiefs coach has come out and said he fears for player welfare, that some performers just don't respond very well to rubber current pitches. And the Harlequins boss, Conor O'Shea, has also identified that he can see why it's useful at a grassroots level, but certainly at international level, he's not sure whether it's a particularly, or worried about the long-term effect on the athletes. So there are both positive and negative sides to this story. If we look at the history, though, of these pitches, in 1966, the first pitch was used in Houston, Texas, in the Astrodome. This was followed by England in the 1980s putting artificial pitches in certain clubs. QPR is a good example. These lasted for a shortish time due to inconsistent quality and issues with safety. By 1994, all pitches had been replaced by natural turf. In 2001, FIFA and UEFA then started to turn this round and developed an industry standard for artificial pitches. And in 2003, during the Male World Cup at under 17 level, one of the 4 host stadiums was equipped with football turf, with 3G turf. This was then followed by the laws of the game stating that we could now certify pitches as 1-star or 2-star, with 2-star pitches being recommended for international matches. And in 2007, at the Under-17 World Cup in Peru, all the games were played on artificial turf. So it has been used at elite international level. Now, we hear a lot about the term 3G, but what does it actually mean? Well, when we look at historically at the first generation pitches, these were basically carpets with a small base with a yarn on the top, and it was the same as running around on a carpet. 2G then was emerged, and rubber crumb or sand infill was used to soften and impact the forces. Now we have 3G, which looks something like this, and we have a layer of shock absorber here. We have underneath it a dynamic base, which may be also, but there may also be some tarmac or macadam here. And then we have an infill that could be a composite of sand or rubber crumb that can influence the impact forces. In the papers, and often when you speak to people that are involved in football and rugby, they talk about 4G. 4G doesn't exist. It's just a marketing ploy. 3G is as far as we've got. 4G is the next level, which would be the next generation, which is going to try and remove rubber crumb. But it's not commercially available. It's experimental, and it doesn't exist. So FIFA then in 2007 also identified preferred turf providers to further enhance the quality of these pitches. The background, though, to replacing, or the rationale for replacing these natural pitches with artificial pitches comes from a variety of reasons. Firstly, the versatility and participation. You can play a number of different team games on them. Hockey, rugby, football, for example, can be played on the same surface. There's an overlap in terms of the mechanical requirements of these pitches. It reduces or negates the effect of environmental influence. If you look at countries like the Scandinavian countries, they've been using artificial pitches for a number of years, and this has allowed them to participate in sport throughout the winter seasons. The economic benefits through reduced maintenance, and also an increased occupancy and inclusion in terms of people participating in sport. Suppliers of sport turf have constantly been developing these various turfs, And there's been significant improvements over the last decade from two main areas. Firstly, materials testing in terms of friction, energy restitution, and torsion testing. And secondly, from player-surface interaction, addressing such questions as injury, fatigue, and technique. And it was the fatigue aspect of this that Mike Hughes and Professor Irwin were involved with Cardiff University. There are four main areas that my research has focused on in turf and this physical environment. Technique analysis that has looked at using cross-sectional type studies, examining the influence of performance and injury, examining the influence of surface temperature on different types of turf, artificial versus natural, different types of artificial turf. It has been a concept of a multi-playing surface, which can be used for both football, hockey, rugby, to try and improve the grassroots level of the sport across countries that potentially can't grow natural turf, so South America, countries from the continent of Africa. And this is